Hello, everybody. Good morning, afternoon, evening, depending on your time zone. So today, what I want to talk to you about is not about the top 10. You're going to have several hundred people over the next 3 years give you their take on what each of the categories means and what you can do about it and all of that, and that's awesome. My job today is to explain to you how we got to this top 10. Like, how did we get to this specific list? So that's what I want to cover. If you've got questions at some point, please throw them in. I'm more than happy to answer them. As one of the OWASP flagship projects, one of the things that we work really hard to do is we try to be really transparent about how we build this project. So if you notice, I am one of 4 co-leads on this team. So it's myself, Andrew Vanderstock, Torsten Gigler, and Neil Smithline. And the 4 of us helped put together the top 10 2017, and we came back together for the 2021. And it's really good, I think. We have a pretty diverse set of backgrounds. So that leads to lots of good spirited discussions about what we should or should not do in different spaces. And then the other thing you can see on the title slide is we have 3 different links. The top 10 itself was released to coincide with the 20th anniversary. And you can see that at owasp.org/top10. Our GitHub project. So every time we make changes or we do a release for review, any issues that people create, responses to them and everything, all of that is publicly available in GitHub. And then we also have a separate project site. So it's a site that gives you more information about how the top 10 is built. And then blog entries. When we're working on it, we will give periodic updates in terms of where we are, what we're working on, what we're looking at, and that's at owasptop10.org. So as we get started, one of the first things I want to cover is we actually have icons. For the first time in the top 10, we actually have our own icons. We're not waiting on other people to determine what kind of icons they want to create for these categories, but we actually have our own. And many thanks to Hugo Costa. So he helped us put up with us because it's actually quite difficult to figure out one image to represent an entire category of vulnerabilities. And so some of these images lend themselves fairly easily, like broken access control. It's not terribly hard to visualize a fence with broken panels. Crypto failures injection is actually quite easy. But then you get into things like insecure design or server-side request forgery. Things like that, all of a sudden it becomes really difficult to try and figure out what one picture can convey the concept of this category. And so we had a lot, and I mean a lot, of discussion over a number of months about what exactly to use for each of these. But I like them up here because I'm excited that we actually have them. So that absolutely helps with messaging. So the question is, on the top 10, how did we get to the release? Like, did we just make it up because we felt like it? Or did we actually have a process that we followed? So the process that we followed is, well, somewhat depicted on this picture. It's meandering. It took us a little while. We were hoping to have a 2020 release, and then we had a fun little pandemic. It's not fun or little, but we had a pandemic. And so we started trying to make a data call and didn't really get much response because people had a lot more important things to deal with. So we decided that we needed to delay the top 10 until 2021 because we wanted to give people the opportunity to be able to take care of things that are really important. And then we would get back to this. So we did. And then we spent, the data call closed near the end of last year. And then we spent several months culling through the data and then trying to figure out like what best represents this next top 10 list. So as we were going through to build the top 10, we had some core principles that we were based on. So we had to remember that the OWASP top 10 is a baseline. It's not a ceiling. It is something that you start with, not something to completely aspire to. It is not a full program. If you manage to accomplish the entire top 10, it is not the end of the road. You've made a milestone. You're partway through your security program. The top 10 was originally built as an awareness document, and it still is for the most part, but it is also a pseudo standard, which makes it in a really strange position in terms of how we build it. Because we also have to understand that when we build a new top 10, what we're putting in motion is tens or hundreds of thousands of hours of work to update tooling, to update training, to update documentation, to update policies, to update all sorts of things that we had never really originally envisioned with the top 10 that would all be impacted with it. So we don't take this lightly. Anytime we go to make a change, it is not, there's nothing that's just haphazard about trying to work on this. The next core principle we looked at is data is good, but data isn't everything. So we wanted to base as much as we could off of data from a data call and a data collection, but at the same time, we didn't want to blindly just work on the data. We needed to take it with a grain of salt and try and understand what was the limitations of that data and then what could it tell us. And one of those things is data looks into the past. So when we make a data call and we get sent data, we have data from multiple different sources, and it's data from 2017 to, we have some that stretched into 2021. But it's not just that the data is for findings of that particular year, it's that there's a delay before data even shows up in the first place. So when human AppSec professionals in the community, we find a new vulnerability, we find a new way of testing something. It takes time for that to become mainstream to the point where it starts showing up in data in any kind of significant manner. So you find stuff, you manage to get some initial testing, you manage to get some initial automation, and then you have to get that automation adopted and widespread across multiple different types of tools and different organizations and different groups. And so it may take years between when you initially figure out one type of vulnerability and then how to look for it, and then the time it takes to refine the tests and then make it go to scale to where we can actually have significant amounts of data that tell us how big of a problem this really is. So this is part of the reason why we do a community survey for the top 10. So we started this in 2017 and we continued it in 2021. That of the top 10, typically 2 of them of the top 10 are picked from the survey. So the idea with the survey is we go and ask people, what do you believe is worthy of being in the top 10 that is not likely to show up in data, either because it's difficult to test for, or it is too new to show up in tests. And so that's why we do the survey, because that's the only way to get the more recent, the now, the upcoming to some extent. And so it's not purely just looking in the past. The other principle we have is stability is good. So when you deal with a standard or a pseudo standard, you don't need that bar to change every 3 or 6 months. We've been asked before, why doesn't the top 10 adopt like a DevOps model? And every month the top 10 could update. And I don't think that person realized how dramatically bad that would be for the top 10. If the top 10 was a constantly moving target, it would no longer be used, because it would be ridiculously frustrating to try and develop training for the top 10 only to have it change on a monthly basis. And so for some things, it makes a lot of sense to make them continuous. Continuous change, continuous build, continuous delivery, and that's great. But for something like the top 10, even every 3 or 4 years, that makes sense. You need that stability to build things on top of. So that's why we do it. We do it, usually the aim is for 3 years, and we have a fallback to 4 if something comes up. But that's generally the cadence for the top 10. The next principle is raising the minimum bar. So when we look at trying to build the top 10 on each iteration, we're trying to figure out when we look at this data, when we look at what's going on, how do we raise the bar? How do we drive the industry to improve? And that feeds into the next one, is we have to be really careful that we drive the right behavior to improve the software security industry. Because what's going to happen is when you have the top 10 and it's a pseudo standard, then people are going to try and build things against it. If we choose the wrong categories, or we choose categories that actually end up causing regression in some spaces, that's the last thing we want to do. So we try to be really careful that what we're going to do, the 10 categories we're going to produce, is actually going to raise that bar for the industry, that it will push people farther to develop in new areas. And then the last one we had, and this isn't new, but it's being more explicit, is we've set out to focus on root cause over symptom. And I'll explain some of that. So in 2017, we went back later and decided to draw basically a somewhat of a Venn diagram of the relationship between the different categories in 2017. And we realized that, in all reality, cross-site scripting is a form of injection. It needed its own category for a while just so that it could have that kind of attention, because it had really high frequency. The data is showing that cross-site scripting is actually in decline at the moment, and I think it's largely because of updates to languages and frameworks. There are some that it's almost non-existent in, and that's awesome. That's the behavior we want to drive. We also look at things like security misconfiguration can cause different types of things. So also remember, this is by title. This is not by like the definition of the category, meaning what CWEs are in the category. But one of the things that showed up on here that was kind of interesting was sensitive data exposure. So broken authentication creates sensitive data exposure. Broken access control can create sensitive data exposure. Misconfiguration can create sensitive data exposure. Sensitive data exposure in itself is the result of something else. It is not a root cause. It is telling you this is the effect. This isn't the cause. And so it came to light, and I started to realize it when I saw like somebody was doing training for sensitive data exposure, and then they said, and we're going to go beyond the top 10 and talk about cryptographic failure, which was the vast majority of what the sensitive data exposure category was. And I was like, all right, we didn't do it well enough. It's not being understood correctly. And so that's part of the reason why we had change and we don't have sensitive data exposure anymore. And the last thing on this that's interesting is I've had people tell me like, well, everything's in A9, because all of these things are in components with known vulnerabilities, sort of. Now, the interesting thing with components with known vulnerabilities is that's third-party code. All the other things are typically first-party code. Those are things that you're directly responsible for versus using something else that somebody else is directly responsible for. So that drove some of the behavior in terms of how we looked at stuff within the top 10. So the one other thing I want to show is like when we're looking at the concept of where does the top 10 fit. So one of the other projects I work on is SAM. So it's the Software Assurance Maturity Model. So within SAM, so this is a exploded graphic of SAM version 2.0. So all the business functions, security practices, their associated streams and activities. So how the top 10 fits into this is the top 10 traditionally is used for the basis to start security requirements. So ASVS gives you a whole lot more detail, but sometimes people start with the top 10. It's easily consumable. It's relatively simple by comparison. It's not the end goal. Again, it is a baseline. But then you have it for software dependencies, related to third-party components, and then you have for control verification. So sometimes also the top 10 a lot of times gets used in policy and standards or training and awareness. And so recently with the new updates, so now the top 10 starts to touch a little bit on threat modeling, a little bit on like secure architecture, a little bit on deployment. So the new software and data integrity category starts talking about things about securing your deployment process. So, but at the same time, notice how little coverage of the entire software assurance maturity model that SAM has that the top 10 actually covers. So just to give you an idea, like this is where its place is. It is not a program. So if we look at the data that helps us build the top 10, one of the things that I really want to make sure I do is I want to say thank you to everyone who contributed data, because everyone here had to expend effort, had to expend time to be able to pull the data together and structure it in the way that we requested. And not every organization, not every vendor, not every group maps their vulnerability data to CWEs by default. So for some of these organizations, they had to go through a decent bit of work to take whatever they had for in-house categorization and then map them to CWEs. So we had 13 contributors, 12 are listed, and 1 requested to be anonymous. So again, thank you for contributing data. If you hadn't, we wouldn't have the top 10 in its current form. We wouldn't know. But these 13 organizations contributed over 500,000 applications worth of vulnerability data. It was amazing. It's the largest group of data that I think we've ever put together in terms of just in one cohesive group. So in that data, one of the things that we continued through from 2017 was looking at incidence rate, not frequency. So one of the things, if you remember in 2017, we shifted from frequency to incidence rate. So frequency was more, hey, if I test an application for cross-site scripting and it has a systemic problem, you could have 4,000 or 5,000 instances of cross-site scripting. Not terribly useful for our purposes. It may be for that app itself. So on a smaller scale, if you're looking at the app itself, knowing that there are 5,000 instances of cross-site scripting means your likelihood is through the roof and you have a systemic problem. You need to find some central control to be able to address this at the application level. However, when I'm trying to look at a global population of applications and try to figure out what percentage of that global population of applications is actually impacted by cross-site scripting, I care much more about incidence rate. I want to know what percentage of applications had at least one instance of cross-site scripting. For my purposes, I don't care if it's 1 or 5,000. That's not the point. And again, that's just because of the way we're looking at things. We're trying to aggregate a bunch of different perspectives together from a bunch of different types of tests. It could be human-based testing, it could be tool-based testing. The thing is you can put those two types of data together if you're looking at incidence rate. You cannot merge human testing and tool testing if you're looking at frequency. Because when humans test things, they will find 2 or 3 instances of it, and they're like, you know what? I don't have the time to find 5,000 or document them. So I will tell you, you have a cross-site scripting problem. Here's 3 examples, and I move on, because that's what I'm paid to do. A program or a testing tool will move on, and it will dutifully identify 5,000 individual points of failure for cross-site scripting. You can't merge those 2 types of data together, because the tool data will absolutely drown the people. So that's why we deal with incidence rate. One of the other things that was interesting in here is when we went in 2017, the data call had like 30 defined CWEs. We asked, hey, for these 30 CWEs, tell me what kind of data you have. And if you have some other ones, please let us know what other ones you think might be interesting. So in general, we had a fairly narrow view. We were looking at things that were more commonly known and understood at the time. For this time around, we said, you know what would be really interesting? If we just said, send us your data. Send us CWEs that you track, that you map against. Because we were really curious to see what was actually out there, because we had this theory that we were missing stuff because we were prescribing which CWEs we had asked for previously. So it opened floodgates. I really did not expect to get almost 400 unique CWEs mapped in the data. So that ended up changing how we built the categories, because no longer did we have categories that were somewhere around 1 to 5 CWEs. So this time around, when we grouped findings together, CWEs together into risk categories, we had an average of 20 CWEs per category, and it would range from 1 to 40. And I'll explain the 1 later. There's a reason for it. But when we asked for data, we said, please, at a minimum, give us this information for a given year, for a given CWE. Tell us how many applications you tested. What was that population? And then how many apps did you find at least one instance of that CWE? And there was other metadata that we asked for. We said, hey, if you can tell us what kind of testing tool, or whether this was a human, whether this was DAST, SAST, IAST, what kind of tool you used, what kind of language, what kind of industry vertical, a number of different things. And so beyond this base set of criteria, we got a variety or varied responses depending on how an organization stored the data. But at a minimum, we had this because we needed this level of minimum data to be able to compare the results against each other. So we had interesting results. So I went back through and I analyzed all the CWEs that we were sent, and there was only one CWE that all 13 organizations said they actually tested for. And that was CWE 79. So if you've played with CWEs, not everybody has, but if you had, you should recognize CWE 79, because CWE 79 is basically cross-site scripting. It is probably one of the easier things to test for and one of the more common things that you can find. So we have a plethora of test cases to be able to test for cross-site scripting. The fun thing is we also use CWE 80, which is also cross-site scripting. Very slight difference between the two, but we found that sometimes people use 79, sometimes they use 80. The second largest one that we had 12 people or 12 organizations test for was CWE 200. So CWE 200 is exposure of sensitive information to an unauthorized actor. So this is, it just sounds like, sensitive data exposure. In reality, if you dig into the details of CWE 200, it is actually a broken access control CWE. It is talking about, in the detail, it talks about broken access control. That's why you expose data. But on the surface, it absolutely, by title, looks like it is more of a symptom CWE. So number 10 had three, or not number 10, the third one down there were 3 CWEs that 10 organizations looked for. And it was 327, which is broken or risky crypto algorithm. 89, which again, if you play with CWEs, you should recognize 89 because that's SQL injection. And then we had 352, which is cross-site request forgery. And then we tail off. And the interesting thing is greater than 75% of the CWEs contributed in our data set were tested at 3 or fewer organizations, which tells me that we differ sometimes greatly on how we map types of vulnerabilities or how we map things to CWEs. And we may differ greatly on how we test for things. And that's an interesting thing in this data. So the other thing I have is limitations on this data. Like, I don't know exactly like what tests you ran, how often the same app was tested. We did ask for retests, like, is this the first time you ever tested the app for that year, or if this was a retest? So our 515,000 apps that we have were all marked as retest no. We have another 300 and some thousand applications that were retest versions of the original applications. But it's kind of interesting to see how differently we decide to map CWEs to different types of vulnerabilities. So if you also remember, we have a community survey. So in this survey, again, we asked, what do you think should be in the top 10 that you think it's unlikely will have data or unlikely to be testable? So number 1 in the survey was cross-site or server-side request forgery, so SSRF. It's really interesting because SSRF was in the data, but if we went by data, SSRF wasn't that big of a problem. So I can guess at why these two don't agree with each other. So some of it may be SSRF is new enough that we're not really that great at testing for it yet. That it's there, but we're not really good at finding it. So this may be a point where the humans tell us, yes, this is a problem. We have seen it. It creates large problems. There's a large impact when we find it. And the humans are better at understanding that it's there and they can find it. And we just haven't taught the automated tools how to find it just as well yet. It may also be that the humans have a bias. And there's been just enough large news stories and Twitter action in the last couple of years that the perception is SSRF is a really big problem. I don't know for sure which one is which, but we'll find out in the next 2 or 3 years when we do this again and we see what the data ends up coming to. Do we improve testing and then we find out, yes, it is a bigger problem? Or does it quietly slide away? I'm not entirely sure. I think it's a bigger deal than the testing data shows, but again, we'll figure it out. The second one in the survey was unmaintained third-party components. So the data was large enough for this particular type of CWE that it actually made it into the top 10 by data, and it didn't need to come in by survey. So the interesting thing is number 3 was insufficient logging and monitoring. So that's an interesting category. When we added it in 2017 by survey, we had some people tell us, oh, you're going to break the top 10. You can't actually test for insufficient logging and monitoring. What does insufficient mean anyway? And it was really interesting to see in 2021 that if people hadn't voted it back in on the survey, it wouldn't have made it in. It just flat out wouldn't, because those are essentially the guidance and the rules that we set forth for how we build it. But people came back and said, you know what, this really is important. This is a category that is really tough to test for. It is hard to determine insufficient logging and monitoring, or we've updated it in 2021. It is now security logging and monitoring failures. It's really important. You're highly unlikely to be exploited through it, but if your application is exploited in some way or you have a breach, if you don't have sufficient logging and monitoring for security events, you're in a heap of trouble. You're in a real trouble identifying who, where, what, when, why. So it's absolutely an important category. So then the other ones we have like unprotected storage of credentials, unrestricted upload of file of dangerous types, excessive attack surface, and so on. The vast majority of these other CWEs are in other categories, because there was some data for them that would show up, and so they got bundled into other categories. So one of the things we want to do is manage likelihood. So if you look at the basic risk calculation, right? Likelihood times impact. So you look at incidence rate, so the number of apps that we find a CWE in versus the number of apps tested for that CWE. We had some interesting scenarios. So if we looked at the data for CWE 552, so files or directories are accessible to external parties. The data we had showed an incidence rate of almost 56%. Of the 11,000 apps tested for, it was found in 6,000 apps. However, the population that we had overall was over 500,000 apps. So in reality, only 2% of our total population that was contributed was really tested for the CWE. So when it was tested for, it was found in essentially half the applications, overall, it really only has an incidence rate of 1.2%. The problem is we're trying to figure out, how is this statistically significant? How likely is this to be an accurate representation of the rest of the population? So what we did is we created another factor. We considered coverage. So coverage is what percent of the population overall was actually tested for a CWE. So this helps us indicate a level of assurance. So if you've only tested 2% of the population for a particular CWE, I'm not as convinced that that is a representative sample. But if you get into things like CWE 200, where it has an incidence rate of almost 20%, which is still significant, but you look at the number of apps tested represented about 94, 95% of the total population. So at that point, I have a high level of assurance that this incidence rate of nearly 20% is accurate. So of our entire population, the vast majority of the apps in that population were tested for this particular CWE. So, but the interesting thing is, again, is I believe looking at the data, it's my analysis that says I think CWE 200 keeps getting used as a catch-all. So anytime sensitive data is exposed, a lot of times that CWE gets assigned to it, not necessarily because we understand the root cause, but we just understand sensitive data got coughed up, or this could cough up sensitive data. And rather than mapping to a CWE that is like the actual reason why sensitive data was exposed, we actually use the CWE that says we expose sensitive data. So one of the other interesting things I wanted to look at in this data is how does the different tooling compare with each other? So this is a topic that gets brought up from time to time where we're looking at what does DAST find versus SAST versus IAST? Like how do they relate to each other? Is there overlap? And so some of the stuff I've seen so far says there's probably 10, 15, 20% overlap between dynamic testing and static testing. IAST crosses over between the other two as well. So in the data that we had that was actually identified as this was a SAST tool, so static analysis, static application security testing type tool, we had certain CWEs. So things like use of hard-coded password. Yeah, absolutely, that's going to be a static analysis. Dynamic analysis isn't going to tell you that. It doesn't look in that way. So that I totally expect to show up in SAST. So these are the top 10 CWEs that show up for tools that were data that was identified coming from a SAST tool. Insufficient entropy. Again, that's really, really hard to test for in a dynamic environment because you would have to do a ton of sampling to try and determine you didn't have sufficient entropy. In the static analysis side, you could absolutely just be like, well, I know that method call is not a proper pseudo-random number generator. You don't have enough entropy. And then that's actually quite easy to spot at a static analysis level. So in dynamic analysis, we can find things like, hey, we've exposed sensitive information to unauthorized actors because we can do access control checks. Sensitive cookies. So this is interesting. So if we look at things that are related to cookies and headers for applications or APIs, this is something that static analysis can't really tell us with any level of confidence because those settings like flags on cookies or the existence of a header, those may not exist in the source code. Those might exist on some network device, might be a WAF, might be a proxy server, might be a web server, might be an app server, might be some kind of external factor to the application itself. Only through dynamic testing can you actually see in the response that went back to the user or the calling system, do we actually see if this exists or not? So there's definitely things that can be found in one or the other that the other type of data testing cannot actually find. So IAST is interesting because IAST is actually generally, from my experience, more accurate because it can actually see what's going on. The challenge with IAST is it doesn't actually have its own testing model. It's dependent on your testing coverage from something else that invokes tests. But it's really good about actually watching what's going on under the covers. So if we've got things going out like input validation, it can trace that and it can give you a lower chance of false positives to determine whether or not something's showing up. So some of these CWEs, you can see that like they're fairly unique to IAST because it has insight into things. So looking at these different top 10s for tools, I was curious, like how much do they overlap? So sensitive data exposure is interesting because half of it comes out of IAST identified tools, a third of it's from DAST, and 16% comes out of a SAST type tool. SQL injection is predominantly static analysis tools. In terms of like, yep, we see it, we do it. I think IAST is probably underrepresented here because IAST would actually be quite useful in identifying whether or not SQL injection would actually work. Cross-site scripting is, I'm not surprised, it's a relatively decent balance. Here, SAST is almost 50%, and IAST and DAST kind of split the rest of it. Looking at things like insufficient entropy, IAST and DAST won't see that. You just don't, it's not really worth testing for that kind of problem in either of those types of testing. That's 100% SAST tool. Clickjacking. Clickjacking is kind of interesting because, again, it is how that result is represented to the user. So in our clickjacking data, it's 100% DAST tool identified as clickjacking. So there's some interesting overlap between the three. I'm still playing with the data. I haven't gotten into like overall percentages, different types of overlap with that. But basically what we come away with is on one hand, I wish I could tell you pick one of the three, you're covered. But in reality, each of them finds unique things that the others can't find. So you kind of need all of them if you want that full coverage. So again, remember, risk is likelihood and impact. I'm not going to get into the fact that we rarely use time and likelihood, so it's kind of incomplete compared to how other industries use risk. That's a topic for something else, but we have likelihood and we need impact. So in 2017, impact was, by definition, we used exploit, we used detectability, which is really kind of likelihood, and then we used impact. But we use technical impact, not business impact, because we can't really tell you business impact on like a generic high-level scale. The data source for exploit and impact and detectability in 2017 was essentially the leadership team. We got together and we had about a 4 or 6 hour meeting where we argued with each other on average, how hard is it to exploit your average SQL injection? How hard is it to, on average, to exploit cross-site scripting? What's the average impact for each of these? And so they were rated on low, medium, high for these different things. So in 2021, we had so much data for likelihood, we really, really wanted to be able to do it for exploit or for impact as well. So what we did is we looked around at what was available, because this isn't data that we could really get in terms of a data call. It wasn't in the data call. We didn't know how these different things were ranked or scored. So we looked through and we said, all right, something that does exist is we can look at CVSS subscores for exploit and impact. Not the overall CVSS score, but the specific subscores for exploit and impact. So what we did is we actually went to OWASP dependency check. And we said, because we knew that it went and pulled all of the data from NVD and it stored it all in a nice little H2 database. And so we set up dependency check, pulled down all the data, queried the tables within it, and pulled out all the data related to CWEs. Anywhere CVE was mapped to CWE. And so we found, of our nearly 400 CWEs, we found that 241 of them had CVE data mapped to them. So not all of the CWEs that we have CVSS subscores that we can actually leverage. One of those examples, like I mentioned, is vulnerable components, because vulnerable components basically will never have a CVE mapped to the CWE for vulnerable components, because the CVE would actually be mapped to the CWE that was the root cause of the problem. So some of those we just had to essentially put in average. So we said, hey, exploit and impact will be 5 on average, because it's not 0 and it's not 10. So I could pick anything in between, but we decided just to pick the simple middle ground. When we look at the top 10 CWEs mapped, the largest individual CWE is actually CWE 79, which is our good friend cross-site scripting, which again has a high frequency. But the interesting thing is 175,000 of the CVEs that we had in that data, 125,000 were mapped to CWEs and 35,000 were unknown. Whenever they were created, somebody didn't map them to a CWE. Only 20 CWEs in that data had more than 1,000 CVEs assigned to them, and only 70 CWEs had more than 100 CVEs assigned to them. 65 of the CWEs only had 1 or 2 CVEs ever actually assigned to them. So this data was from August of this year. So it's changed a little bit since then, because right now we have essentially the largest creation of CVEs that we've seen yet. But we also had to look at in CVSS scoring. So the data we had was almost evenly split out of NVD of CVSS V2 versus V3 scoring. And if you look at the two, they don't actually line up with each other. So CVSS V2 subscores for impact would range from essentially 3 to 10. But if you looked at version 3 scores, it would range from about 1.2, 1.3 to 6. And the reason for this was they changed the formula on how they actually built the CVSS score between version 2 and version 3. In version 2, impact and exploit could technically or theoretically be 0 to 10. Then they would take 40% and 60% of those, knock them down by 0.4 or 0.6, and then they would to get their total together. So in version 3, they actually artificially limited them. So impact could only actually max out from 0 to 6, and exploit could actually do 0 to 4. So basically, I had to look at those and essentially normalize them so that they would fit along a similar scale, so I could see that. However, what made it interesting is even after normalization, the other changes in terms of the process of how you score something, on average, in version 3 of CVSS, impact scores average 1.5, 1.3 points or so higher on average for CWEs. Something similar in exploit. So in exploit, you have a range typically in version 2 of somewhere around 4 to 10 in terms of the scores. In version 3, your score range is essentially 1 to 4. This one's a little bit more of a dramatic difference location, but it's the same reason, just because of the way they changed how they scored and what range was possible within the subscores. If you look at these, though, within exploit deltas, version 3 on average was almost half a point lower for CWEs. Also, part of the reason why your amplitude changes from left to right on these are ordered left to right in terms of the highest frequency to the lowest frequency. So when you get down to a really small frequency, you have much higher deltas between them. So we have our data porridge per se. So we now have incidence rate and testing coverage for likelihood. We have exploit and impact, the subscores for CVSS that count for impact. But we also decided essentially to season it with a little bit of total occurrences. So there was some weight for actually the number of times you would find a particular type of CWE. So then we would average these together. And then we went back and forth. So when we started trying to put CWEs into categories, we actually spent about 3 months working on it, because CWEs don't cleanly go into some of these categories, depending on the day, depending on what you're looking at. Sometimes it makes more sense to go into one category or another. We move things around between different categories, just trying to figure out what made the most sense. And I read through the detailed description of 400 CWEs, trying to figure out like what was the root cause of the CWE, what was it going after, what type of CWE was it when we grouped it. So we ended up with basically this type of formula. So we had different types, we had our different categories, and then we had our incidence rate, our coverage, exploit, impact, number of occurrences, and then a total score. So what we decided to do is not pick average, but pick high watermark for CWEs within for incidence level. Because I have an issue with averages have a tendency to hide the edges. They hide different impactful levels for high and low, below, above and below average. So the industry essentially has pretty much a precedence for using high watermark. Like if you look at NIST data categorization, it's the high watermark of data. So there's a lot of other things. So we looked at a number of scenarios. We looked at what happens if we do average. We looked at what happens if we do high watermark. And we decided that high watermark represented it better. It was more accurate, more defensible from our perspective. And then I also broke it down a little bit for like contributors or contributions. So what percentage of your overall score did the different elements within the formula contribute? Because I just wanted to see within these categories, where were they getting their points from? Like what was contributing to it? So now that we've built everything and we pushed it out, like where do we go from here? So the top 10 2021 was released on September 24th to coincide with the 20th anniversary. So what do we do now? Like what's next? So from my perspective, we need to get more consistent with CWEs. We actually have a number of CWEs that were contributed that were actually marked as retired or archived. And MITRE had mentions in there that says, please don't use these. These are no longer active. They've been deemed either incorrect or superseded by something else, but yet we still map stuff to them. We also have within CWEs, there's a hierarchy. So there are some CWEs that are essentially categories, and they have multiple layers within a tree down for different types of for different types of CWEs, so that you essentially have parent and child relationships. So try not to map to the highest level, because that kind of obscures what is actually going on. Try to find the most detailed and most descriptive CWE to try and just match up to the vulnerabilities that you find. Also try to use root cause CWEs as much as possible, because root cause is super important to where we can understand, how do we fix this? Symptoms don't help us understand how to fix things, root causes do. Some of the behavior we're trying to drive to is fix this at the language and framework level. Back in 2007, Andrew Vanderstockel told a story about how he added cross-site request forgery into the top 10 list, because essentially at the time, almost 100% of web applications were susceptible to cross-site request forgery. Now that number is in the single digits. Like the data we see is less than 10% of applications are susceptible to cross-site request forgery, which is awesome. So that took, I mean, it's been 14 years, I hope so. But you could also argue we've known how to fix SQL injection for over a decade, and we still have it. It is still one of the most larger reasons for data breaches. But the thing is we can't expect developers to remember all of these tiny nitty-gritty details. We've got to fix these things at the language and framework level. We have to do as much as we can for developers so that by default, they can write secure code. They have to go out of their way to break things. Don't shift left. Expand, like move left. We use language move left instead of shift left, because what happens in the industry is the majority of the time we use the term shift left, we don't actually mean going before code. We just mean earlier in the code phase, When in reality, security needs to exist at the operational level, and security has to exist before you ever write code. When you write user stories, when you do threat modeling, when you do design analysis, design review, you need to figure out security needs to be part of that mindset and that concept at that stage before you ever write a line of code. And that's where the second bullet also fits in. There's a lot of security outside of code. We have to stop being fixated on purely code. And I get it, because at the code level, it's machine readable. Before you create code, it's really hard to do any kind of automation, hard to do scale, because it is still in the squishy human phase where it's more of an art than a science. But the hope is things like insecure design drives a renaissance into threat modeling. And I'm watching it start to come up and occur, and more people are like, this makes a lot of sense. We need to focus in this area. And I'm hoping in 3 or 4 years, we see a big change and a big growth in the threat modeling space, because we have a lot of work to do there. But that's what I have. That's my time. So thank you so much. If you all have any questions, please let me know.